Hi, good morning. My name is Sourabh Agarwal, and I work as a program manager within the SQL Server engineering team at Microsoft. I lead program management for Azure SQL Edge, and I'm excited at the opportunity to talk about the features and the capabilities in Azure SQL Edge and why Azure SQL Edge is the ideal platform for all your IoT and edge computing requirements. In the next 50 minutes or so, we'll talk about the capabilities of the product and also talk about some of the customer scenarios and how our customers are adopting the product to solve their IoT and edge computing needs. So before we talk about Azure SQL Edge and take a look at some of the capabilities being offered by the product, let's spend some time talking about the IoT landscape and how IoT is helping transform the industries as we know it today. If you look at any of the major industry verticals, whether it's manufacturing, healthcare, automotive, financial, or even in the consumer space around smart buildings and home security, IoT has a presence in almost every single industry vertical. And it's not just that IoT has a presence, IoT is helping these industries transform and meet the requirements of their customers. For example, if you look at the manufacturing industry, the usage of IoT or industrial IoT, as you would hear some people say, is helping manufacturers reduce cost. It's helping them reduce security hazards. It's helping them optimize and their distribution and supply chains. It's also helping them meet the current demands of their customers and also improve their interactions with their customers. Similarly, in the healthcare space, IoT is helping healthcare providers connect their patients in remote and rural areas with doctors from around the world. IoT is also helping in the inventions or the propagation of mobile healthcare devices, which are making gathering of health statistics quite easy for people who cannot make that trip to the nearest pharmacy or to the nearest provider. Similarly, in the commercial space, IoT is helping us optimize our homes to be more secure and to be more efficient when it comes to energy usage and other factors. The usage of IoT in the various industry segments has grown tremendously over the last 5-6 years, and it's expected to grow at a very fast pace in the next 5 years. Gartner predicts that almost 80 billion connected devices would be available by the end of 2025, and these 80 billion devices would be generating data to the tune of 180 gigabytes in the next 5 to 10 years. Now, this growth in data and the number of IoT devices poses its own challenges. We'll talk about the challenges in a bit, but let's try and understand what is helping this growth in the IoT segment. The first thing is the availability of cheaper hardware. We have more compute power available in smaller chips now than it was available 10 years ago. And that computing power has become cheaper steadily over the last 10-12 years. Similarly, there is innovation in the space of 5G, innovation in the space of mesh technologies, which is helping these IoT deployments become more prevalent. Now, talking about the challenges itself, the challenges associated with the IoT sector can be categorized into two broader buckets. One is related to the network and infrastructure. The second is with respect to the data itself. Let's talk about network and infrastructure first. By network and infrastructure, I mean primarily the network connectivity and the infrastructure needed to establish network connectivity. There are still regions in this world or on the planet where network connectivity is not yet available. And if it's available, the bandwidth is either too low or the cost is too prohibitive to be able to send high volume of data through that network. 5G promises to solve some of these problems, but availability and cost would still be a factor. Then the second aspect is with respect to the data. Given the growth in the IoT devices and the growth in the volume of data generated from these IoT devices, it's impractical to take all of that raw data and send it to a cloud or a data center target. Essentially, what needs to happen is you take this data and you process this data at the origin itself before that data can be moved to a cloud target or a data center target. Now, the second important thing is in terms of security. As more and more devices gets added to your infrastructure, that many more number of endpoints are exposed. And it becomes really important for organizations to be able to secure each and every endpoint and the data originating from these endpoints so that it does not get in the hands of some rogue user or some rogue element. The third thing is with respect to real-time analysis. There are applications of IoT, especially in the context of a connected vehicle or an autonomous vehicle, or in the context of an oil rig, or in the context of the energy sector, where real-time analysis of this data is very important. And it is not practical to wait for the data to be shipped to a cloud or a data center target for it to be processed first, and then you take the actions on the edge or on the IoT side of the world. The last but not the least is the scale and perf aspects of your data needs. Given the volume of data originating from these IoT devices, and the fact that you need to process this data on at the point of origin itself, scale and performance becomes very important. And as such, you need to invest in technologies or products which provide you that scale and performance to meet your IoT requirements. This is where Azure SQL Edge comes into play. Azure SQL Edge has been designed keeping in mind the challenges which IoT industry or the IoT segment faces today. The features in Azure SQL Edge are built and optimized to help you solve some of these IoT scenarios. Azure SQL Edge is built using the same SQL engine which powers Microsoft SQL Server and Azure SQL. And it is designed to run on these smaller edge servers, edge gateways, and IoT devices. When I say IoT devices, it does not mean very small, low computing power devices, but essentially devices in the range of 2 cores, a few gigs of memory, where you can run a database platform. Azure SQL Edge can run not only on Intel and AMD processors or devices, but it can also run on ARM Pro64 processors. One of the biggest benefits of Azure SQL Edge, and given the fact that it's built on the same SQL engine as Microsoft SQL Server and Azure SQL, is the Perf security management capabilities which are offered by the platform across the spectrum of devices. So you take the application, or whether you are running in Azure or you're running on premises with Microsoft SQL Server, or now you are running Azure SQL on the edge, you get a similar surface area in terms of both programming, management, performance, and security capabilities, which makes it very easy for you to extend your current skill sets and your current applications to the edge. Azure SQL Edge is designed to be deployed in either a connected scenario, and we'll talk more about the connected scenario in a bit, in a semi-connected scenario, or in a totally disconnected air-gapped scenario. We'll talk about the disconnected scenarios also in a bit. The primary objective here is, no matter the deployment aspect or the nature of the deployment, Azure SQL Edge should offer the exact same capabilities and performance and scale. So what do we mean by the connected scenario? In the connected scenario, or the way we define a connected scenario, is when Azure SQL Edge is deployed through IoT Edge and IoT Hub as an IoT Edge module. The disconnected scenario is when SQL Edge is deployed as a standalone container on top of a Docker host or on a Kubernetes platform. The objectives are to provide the same capabilities and experience across the two different deployment platforms or deployment scenarios. So let's take a closer look at some of the capabilities which are offered by the product. Azure SQL Edge uses a fully containerized deployment mechanism in the sense that it is only available as containers, and that's Linux containers today. These containers can run on Intel platforms or AMD platform or an ARM64 platform, giving you the range of or the choice of devices to run SQL Edge on and create your IoT solution. Second, SQL Edge offers native data movement capabilities to Azure. The objective is that you have all of this data on your IoT devices or on your edge computing devices. And once you have processed that data, you want that data to be stored for long-term retention and scale analytics. That's where the data movement capabilities of Azure SQL Edge come into play. We offer capabilities through both the streaming layer and through the batch processing layer to move data as a continuous stream or as a batch to Azure targets. And this data movement is bidirectional in the sense that you can move data from SQL Edge to one of the cloud targets in Azure, be it Cosmos DB, be it Blob Storage, be it Synapse, be it Azure SQL, or any other data services in Azure, and also at the same time bring data down from Azure to your edge devices. Think about a scenario where you have some reference data sitting in one of your cloud databases, and you want to bring that data down to your edge devices for processing, right? That's where the data movement capabilities come into play. The third thing we are bringing to Azure SQL Edge is the same performance and security characteristics of Azure SQL and Microsoft SQL Server. We have taken all the security features from Microsoft SQL Server and we have incorporated those into Azure SQL Edge. So things like transparent data encryption, always encrypted, your row-level security, data masking, all of those characteristics or capabilities are present in Azure SQL Edge. Similarly, in terms of performance, we have taken performance aspects of Microsoft SQL Server or Azure SQL, which makes sense for an IoT Edge sort of deployment, and we have brought it to Azure SQL Edge. So for example, we have things like fast recovery, accelerated database recovery, your column store indexing, compression, all of those enabled by default in Azure SQL Edge. Azure SQL Edge also introduces new capabilities around data streaming and time series. Data streaming capabilities in Azure SQL Edge are powered by the same engine which is used for Azure Stream Analytics and provides similar capabilities as Azure Stream Analytics. We are constantly working on improving or adding the number of source and target pairs which can be used for streaming data to SQL Edge and from SQL Edge. Today we support streaming from IoT Hubs, IoT Edge Hub, and Kafka. And in the future we have plans to add more streaming source target pairs. The time series capabilities in Azure SQL Edge is twofold. One, the capabilities offered by the streaming layer, where we provide native capabilities around tumbling windowed aggregation, anomaly detection, windowed analysis of data and stuff like that. And then there is capabilities which are being added to the SQL engine around time series specific functions and time series specific storage optimizations. We'll look at some of the time series specific optimizations or capabilities which we are adding in a bit. Azure SQL Edge also offers built-in ML inferencing capabilities, in the sense that Azure SQL Edge ships with its own implementation of the ONNX runtime, that is the Open Neural Network Exchange runtime, which provides you the ability to train and test your models in a language or toolkit of your choice. And as long as the models can be converted into an ONNX framework compatible model, those models can be deployed to Azure SQL Edge for inferencing on the edge. The scenario which we are trying to solve for is you train and test your model in the cloud or in your data center, and then once the model has been trained and you have enough confidence on the quality or the accuracy of the model, that model can be deployed to your Azure SQL Edge and run inferencing on all the IoT data which you are capturing with Azure SQL Edge. We are also working on providing capabilities which would allow you to do model management within Azure SQL Edge. So essentially, provide you capabilities which will allow you to take models from a repository or a registry, understand if that model is better or worse than the one currently deployed to your Azure SQL Edge, and take a choice or take a call on whether you want to deploy that new model or not. So some of those things are in plans and would be available in the future versions of Azure SQL Edge. With that, let's look at some of the capabilities of Azure SQL Edge and how they can be used to create an IoT solution. In the first demo, we'll look at data streaming, specifically streaming from a Kafka server. For the purpose of this demo, I'm using the same infrastructure which was used by Bob during his keynote. In this case, we have machine telemetry data being piped to a Kafka server, and then from there being read into SQL Edge using the streaming capabilities of SQL. And then once that data has been read in SQL, we perform anomaly detection and ML inferencing on that data. So let me go ahead and switch my screen from the PowerPoint to the demo environment. So here I have a connection to my IoT machine or IoT device where all my demo modules are running. So the first thing we have running on the device is a Kafka machine telemetry module, which basically emits machine telemetry data to the Kafka server. Let me go ahead and run a quick Docker logs output on the machine telemetry data to show you the output which is being generated by the machine, or the telemetry data which is being generated. So we have this data coming in every few seconds, and there are about 10 different values which are being generated as part of this demo environment. So we have machine pressure, machine rotation, the vibration, and the machine ID, the timestamp, all of those data being emitted by the app or the module, and that data is being sent to a Kafka server. Now, this data, once it reaches the Kafka server, from there it is being read by the SQL module using the streaming layer. And what you see over here is the statistics of the streaming module. I'll talk more about what this statistics, and where are these statistics coming in from. But for the purpose of the discussion, let's stick to the fact that these are the statistics, the streaming statistics from the Kafka server. What you do see over here is the number of input events which were read from the Kafka server, the number of output events which are basically written to SQL, and I'll talk about why there is a difference between the number of events being read and the number of events being outputted to the SQL table. Right? And then you have other matrices around if there were any errors, what is the size of the inputs, what was the size of the output, so on and so forth. Right? Now, where is this statistics coming from? So let's switch back to my SQL Server Management Studio. So what I've done for the purpose of this demo is I've created a streaming job within SQL where the streaming job is called telemetry data. Now this streaming job is running two different stream queries. The first stream query is this one with the with statement. So essentially what it is doing is it's creating a sort of a pseudo table or a pseudo CTE table on the inputs from the Kafka server, and then it does anomaly detection on that data. And we are using two built-in anomaly detection functions. One is the spike and dip, and the other one is called the change point, to determine if there are any anomalies in the data being captured. For the purpose of this demo, I have kept the accuracy rate to 95, which is basically you look at there should be a 95% accuracy in the anomalies detected. And I've also set the limit duration to about 30 milliseconds, which essentially means that it will look at the last 30 seconds of data to figure out if there is an anomaly or not. Right? And then once I have identified the anomaly or if or not there is an anomaly, that data is being written to a SQL table. In this case, it's being written to my SQL table called machine anomalies. The second query as part of my streaming job is a raw data dump of this telemetry output into the machine input table. The machine inputs into the telemetry output table, and this telemetry output table corresponds to the telemetry table in the database. Right, so that's my streaming job. It's taking the data from my Kafka server. We are doing windowed aggregation on this data. So in this case, I am aggregating the last 10 seconds of data using the tumbling window function. And then I'm also doing anomaly detection on that data while the data is being read in. And then at the same time, I'm also dumping the raw data for future references. Right, so if you look at let's go and look at the output from these tables. So for my telemetry table, I can go ahead and dump the last 10 records to see what were the data captured. So you would see that there is the voltage, the rotation, the pressure, the vibration, and if there were any error matrices captured as part of the machine telemetry. And then I can run a similar query on my machine anomalies data to figure out if there were any anomalies. And as you can see, for all the machines in the last 10 seconds or so, we have identified some anomaly in the pressure data, whereas on the vibration data, there is no anomaly. Right. So in this demo, we saw how you can use the streaming capabilities of Azure SQL Edge to read data from a Kafka server and then also perform windowed aggregation, anomaly detection, and at the same time also dump raw data into a table in SQL. In the second demo, we will look at retention policy-based data cleanup. Now, collection and storage of data from connected IoT devices is important to derive and gain operational and business insights from this data. However, given the volume of data originating from these devices, it becomes important for organizations and enterprises to carefully plan the amount of data they want to retain and at what granularity. Right? While retaining all of this data is desirable, it's not always practical. Right? So to address some of those scenarios in Azure SQL Edge CTP 2.3, we introduced a new feature called data retention policy. And once the data retention policy has been defined on a database or a table, there is a background task which runs to clean up old obsolete data from these tables. Let's take a look at this feature in action. So setting data retention on a database or a table is fairly easy. It's as simple as a single alter database or an alter table command. So in the example over here, let's go ahead and create a database which we will use for data retention tests. So let me go ahead and do that. And then once the database has been created, or if there is an existing database, you can set data retention on that database using the alter database set data retention on or off command. Now, to check if the database has been enabled for data retention or not, you can run a query on sys databases and there is a column we have added, is data retention enabled, which would be set to either 0 or 1 depending on whether data retention has been set on the table or not. So in this case, we can see that data retention has been set on the database data retention test. So let's go ahead and create some tables in this database. So the first table I'm creating is a table with a primary key clustered index. And if you notice the new syntax, we are enabling data retention on this table with the command data deletion equals to on. And then we are also specifying a filter column based on which SQL will determine if the rows are obsolete or not. And then the last parameter we are defining is called the retention period, which essentially defines at what period the rows become obsolete. So let me go ahead and run that. And then similarly, I'm creating another table which is unique non-clustered index with the same syntax. The data retention or data deletion equals to on, filter column equals to a date time column, and retention period in this case is 1 week. And the third thing I'm doing is I'm creating a table with a clustered column store index and defining a retention period of 1 week on the table. Now, if you run a query against sys.tables, you would see that the output of there are few columns added to sys.tables which define the retention period, the retention units, and the unit description for data retention. And if you want to run a query on sys.columns, there is a new column added to sys.columns which tells you whether or not a column is being used as the filter column for data deletion or not. Right, so let's go ahead and insert some data into this table. So the first thing I'll do is I'll go ahead and insert 5 records into my data retention table 1, which was my primary key clustered index table. Now, and let me go ahead and run checkpoint. In SQL Edge, the default recovery level is, or the recovery model is simple. So I want to get rid of my log records for the time being. Now let's go ahead and look at my log and see if there are any records. So there you see only 3 records, which is what was written by the checkpoint operation. Now let's go ahead and call the manual cleanup operation on this task. In our case, we had set the retention period to 1 day, so automatic data cleanup won't run, but we can always go ahead and run the manual cleanup operation on that table. So in this case, I'm specifying the table on which the manual cleanup should run, and this is an optional parameter which outputs the number of rows deleted. And we can go and check that there were 5 rows and you have 5 new log records indicating that 5 rows were deleted from the table. Now let's do the same thing on a column store index table. So let me go ahead and insert 5 rows into this table and alter the index. That is basically rebuild the index. Now what this will do is it will close the row group with the 5 rows in it and compress the row group. We can go and check this using the sys.columnStore row groups catalog view, and you can see that my table has 1 row group which is in the compressed state. Let's add 5 new records into the tables for a total of 10 records in the table now. So if you notice the output of sys.columnStore row groups now, you have 2 row groups in the table. One is in the open state, the other one is in the compressed state, and both have 5 rows in it. Let's go ahead and make sure that there is no checkpoint and all that. Now let's go ahead and run the manual cleanup task on this table. So you would notice that there are 10 rows which were cleaned up by the manual cleanup task, which essentially means that rows in both the compressed row group and the open row group were deleted by the manual cleanup task. Now these are obviously rows which were outside of the retention period, because if you notice my query, I had inserted rows which are at least 10 days older, right? So now let's go ahead and run a query on my row groups, and you would notice that both the row groups, the data has been deleted. In the compressed row group case, the rows have been marked for deletion using the delete bitmap. If I rerun my alter index rebuild operation, this would clear all the deleted and ghost records from the table and results in a column store index with 0 row groups. And if you have to disable data retention on a table or a database, you can run the alter table command to set data deletion equals to off. Similarly, you can set data deletion or data retention equals to off for a database. So in this demo, we saw how easy it is to set data retention policies on your databases and tables and use those policies to automatically purge obsolete data from the database. Today, the implementation uses delete queries and column store optimizations. We are still working on improving the delete query performance and how we optimize the performance of this purging on HOBT indexes. In the next demo, we will look at how machine learning based inferencing happens in SQL Edge. For the purpose of this demo, we will train a Mlp classifier, basically the multi-layer perceptron classifier using the sklearn neural network package in Python, and then deploy that model to SQL Edge to run inferencing. For the purpose of this demo, I'll be using the ECG classification data to train my model and run inferencing on my model. So what I have here is Azure Data Studio with a Python notebook running in Azure Data Studio. And for the purpose of this model training, let's import some Python packages which are needed for the purpose of the training. So in this case, I am importing Python packages like the pandas, the pyodbc, the sklearn packages which we will use for the training, and then the rest of the packages around Onyx and Onyx runtime. And then let's also pull in some data for our model training. This data is coming in from my Azure SQL Database Edge instance, and this is the ECG classification training data from MIT. So this takes about 30 odd seconds to read all the data from the database. This is approximately around 100,000 odd records with different classification data. And then once the data has been imported into the data frame, we will run a basic redistribution or resampling of the data so that I have equal samples for all the different types of classification we will work on. Once that classification has been done, I'll distribute my table or the data frame into training data set and testing data set. And in the next step, we are creating a model pipeline where the first step of the pipeline is to do a column transformation, and the next step of the pipeline is to run the Mlp classifier, which is basically the multi-layer perceptron classifier. This is one of the neural network classifier functions available in the sklearn package. So let me go ahead and do that. This takes about 30 odd seconds also, primarily because I have reduced the number of max iterations. You can go to a higher number, but that would in turn take longer time for the model to be evaluated and to be available for rest of the steps. So let's give it a couple of seconds or a few seconds to let the model train and run through the iterations. Then once the model has been trained, we run two quick steps to check the score and the accuracy of the model. In this case, I am using the model.score parameter to identify what was the score of the model. And in the second case, I am using my training data set, or the output from the training data set, along with the actual output from the training data set, to understand what was the R2 score between the predicted output and the actual output. So you notice that my model has been trained. Let's go ahead and look at the score of the model. So the score of the model indicates about 0.89, which is fairly okay. If I were to increase the iterations a bit more, I might get a higher accuracy of the model. Let's go ahead and run this query also. You would notice that the R2 score is around 0.77, which is fairly okay, and the mean root square error is about 0.45, which is also decent. The next step of the model is where we will convert the model into a Onyx compatible model and save that model. So I'm saving that model as a ECG model sklearn on my disk, which I can use later to go through the characteristics of the model. Now, for the purpose of this demo, we are going to write this model into the models table of my SQL database. So let me go ahead and do that. This will write the model as a var binary input, or a var binary field, into the models table. Now, once the model has been written into my SQL table, I can go back to my SQL table and run machine learning based inferencing on the data. So for the purpose of this data, I have a generated data set from my ECG module, and I'm going to run inferencing on that. And in this case, I'm going to get the last 10 rows of the data and run inferencing on that. So let me go ahead and run that. Oops, sorry, I didn't realize I was not. So my inferencing ran on that data, and for majority of the data set, it identified the ECG classification of 1, and then for a few data points, it classified it as a normal ECG reading. So in this demo, we saw how you can train a model or a machine learning model in Python using one of the Python packages, and then deploy that model to Azure SQL Edge for inferencing. Now, so to quickly recap, Azure SQL Edge offers a breadth of features and capabilities which makes it the ideal platform for IoT and edge computing requirements. Azure SQL Edge offers built-in time series capabilities, data streaming and AI capabilities, data movement capabilities, and also offers you unparalleled security and performance, at the same time offering you a choice of platform on where you want to run Azure SQL Edge. And given that it's built on the same engine as Azure SQL and Microsoft SQL Server, it enables a consistent app ecosystem from the cloud to the edge. Given that built using the same engine as Microsoft SQL Server and Azure SQL, you can take your application from one end of the spectrum and to the other end with very minimal changes. Now let's look at some of the customers who have adopted SQL Edge and how they are using SQL Edge. So the first scenario we'll talk about is Carl Zeiss. Carl Zeiss is a pioneer in the space of optics and lens manufacturing based out of Germany, and they are known for their precision and high quality lenses. Their lenses are used not just for commercial or consumer purposes, but also they have applications in high-end military grade equipment, research equipment, and scientific equipments. What Carl Zeiss is using SQL Edge is to build a smart manufacturing solution where the intention is to digitize every single operation or every single aspect of their manufacturing process. That is, be able to capture telemetry data from each and every machine running on their assembly floor to derive efficiency and to derive your precision of the lenses being built or being developed. They are using SQL Edge to store telemetry data from each of these machines, and then using that data to run ML inferencing to analyze if there was a failure in any of the layers of the manufacturing process, or if there was an error in the way the lens was supposed to be cut, or if there was an error in the precision of the lens measurements. Using SQL Edge and being able to capture all of this telemetry data, Zeiss is able to derive almost 20% improvement in the overall efficiency of their manufacturing process. The next customer we will look at is Fugro. Fugro is a geospatial data collection company based out of the UK. They specialize in collecting environmental data from different regions of the planet. Fugro, when they send out these vessels on the sea, or in the sea or on the land or whatever it is, to help collect environmental data, geospatial data, which can then be analyzed to provide reports to their end customers. Now, when Fugro sends out these vessels to the sea or to the land, most of the time they do not have connectivity on these vehicles. As such, it was difficult for them to capture all of these telemetry data and be able to analyze that data in real time or in almost real time. They had to wait for the vessels to dock back and then take that data into their offices before they could analyze. Now with SQL Edge running on the vessels, they are able to analyze all of this data right where it is collected. And then when they establish connectivity using satellite links, they are able to send this data back to their customers or to their head offices in no time. Earlier, a process which used to take them 2 weeks now takes them under 8 minutes to get the first set of reports. That's possible because of running SQL Edge right on the vessels where the environment or the geospatial data is being collected. The third customer scenario we'll look at is from Achilles, a leading plastic film manufacturer based out of the US. Now, the plastic films manufactured by Achilles have usage in different industry verticals. One of the primary usage is in the healthcare industry, where the plastic films are used to build urine bags, IV tubes, blood packets, and so on and so forth. And in response to the global pandemic because of COVID-19, Achilles was looking to improve their efficiency and ramp up the production from their factories. They reverted to SQL Edge as an embeddable offline disconnected data source to store machine information and to have their crew capture that machine specific information and store that on to SQL Edge through their Achilles shop floor data collection system. The essence of the shop floor data collection system is that Achilles uses multiple predefined jobs or job settings to control the production of the films or the plastic films. And each of these settings are stored in an on-premises SQL server sitting in their central IT system. Now, earlier, without SQL Edge, they had to get printouts or have the crew manually note down the settings for each of these machines and then go and apply those settings. Now with SQL Edge and the data movement capability between SQL Edge and between SQL Server and Azure SQL Edge, they are able to sync these machine setting information between SQL Server and SQL Edge and then easily apply those settings to the machines to control production and production parameters. Additionally, while the crew is on rotation or on the manufacturing floor, when they walk past a machine and they are capturing telemetry data from the machine, they can store that data directly into the SQL Edge instance through their front-end app, and then that data gets synced to their central SQL Server environment. Achilles, through the usage of SQL Server and Azure SQL Edge, was able to drive significant improvement in the efficiency of their systems. So we talked about 3 customers from 3 different geographies and 3 different industry segments. Now, in majority of the cases, the deployment pattern being used by the customers are will either align to the connected reference architecture which we have, or the disconnected reference architecture. In the case of a connected deployment, as I had mentioned earlier, the deployment is through through Azure IoT Edge and through Azure IoT Hub. So SQL Edge gets deployed as a module for IoT Edge, and all the data which is being processed and captured by SQL Edge, that data can be moved to a cloud or a data center target using ADF or the built-in streaming capabilities. Now, once that data is in Azure, whether it's in Cosmos DB or storage or Synapse or ADLS, that data can be analyzed to drive scale analytics and to drive insights which can help transform the business. In the case of a disconnected scenario, the setup is quite simple. That is, SQL Edge is deployed as a standalone module, and you can use either Kafka or a Kafka equivalent to stream machine telemetry data or to specific IoT data to SQL Edge, and then run your visualizations, ML inferencing directly from SQL Edge running on your edge devices. So with that, we come to the end of our session today. We talked about the landscape of IoT, how Azure SQL Edge is solving some of the challenges which IoT industries or the IoT solutions are facing. And then we also looked at some of the capabilities of SQL Edge. And then finally, we talked about the customer scenarios and the reference architectures for SQL Edge. In closing, if you are interested to learn more about SQL Edge, please refer to the link at https://aka.ms/SQL-Edge. We have online documentation available on docs.azure.com, and we also have a few white papers available for SQL Edge, which talks about the use case scenarios for SQL Edge. And then you can also go and find the 3 case studies we talked about at customers.microsoft.com. Thank you and have a great day ahead.